In this video, we're going to derive the state space equations for the two-link pendulum. Now, the two-link pendulum has a set of dynamics equations, and from those, we'll get the state space. These are the dynamics equations, and we derived these in a previous video. So click the link to view that video if you want to see how we got these. But for state space, we need to put it into state space form. X dot equals AX plus BU, where X is the state vector and U is the input vector. A and B are the coefficient matrices. Now note that in here, since X is the state vector, that is not necessarily the actual X coordinate. That is just a representative of all the things that could be inside of X. So we actually will have to choose those. Now, how many state variables do you have? One for every energy storage element. Energy storage elements are masses and springs. In this example, we do not have any springs. We have two masses, M1 and M2, each link. So we'll need two state variables. So we'll need X1 and X2. Now, the state space equations are basically a way to write any differential equations in the form of first order differential equations. So that means that we can only go to the first derivative. Now, in these equations that we're given the dynamics equations that we have, those we have a second derivative. So we need to eliminate that second derivative and write this all in terms of first and zero order derivatives. So we're going to say that since we have a first derivative and a second derivative, we'll call x1 equals theta 1 dot and x2 equals theta 2 dot. So now we can say that then x1 dot equals theta 1 double dot and x2 dot equals theta 2 double dot. So we basically just made new variables that represent those variables that we already had. Now we need to rearrange this and get it into state space form. So we need to, first let's replace all of these variables with the state variables, and then we'll rearrange to get it into the proper form. So here we'll have tau 1, tau 2 equals, we'll just call this M times theta 1 double dot is x1 dot. Theta 2 double dot is x2 dot. Plus, we'll say C, and then multiply by theta 1 dot, which is x1, and theta 2 dot, which is x2. So you can see, and then we'll add G. Okay, so you can see here that now this is in a first order form. We just made our state variables the first derivatives, and so then the derivative of the state variable is the second derivative, but it's all hidden. So now we need to rearrange this and get the x dots by themselves. So I'll write it out still using these, the M, C, G for the matrices, and then I'll show you how would you, once we put all of the actual smaller matrix variables back in it. So we need to get x1 dot, x2 dot on one side by itself. So we'll say x1 dot, x2 dot equals, and then this C will go to the other side. So we'll have minus C over M times x1, x2 minus G over M plus 1 over M times tau 1, tau 2. So one thing to note here is that we have this extra G over M term. So we've got here, this is the X dot. Then we've got, this is A, X, B, U. But we have the extra term, the negative G over M. So that actually is because this is not a linear system. So we're not going to be able to make linear state space equations for this. If you wanted to make linear state space equations for this, you would have to actually linearize the pendulum. So if you linearize thetas, because G contains like sine or cosine of theta, that kind of stuff. Theta is buried inside of a trig function. If you wanted to linearize the thetas, you would have to say sine theta is equivalent to theta, and cosine theta is equivalent to 1, which if you're only looking at small angles is fine. But for something like this, where either theta could go from 0 to 360, then you can't use that small angle approximation. So there's no way to get linear state space equations for this, but we're going to get as close as we can. Now, also because these are matrices, but we've written them as scalars, we're going to have to expand this some. So matrix inverse. For a matrix that is A, B, C, D, if we want to take the inverse of it, that is 1 over the determinant times D, A minus C minus B, which is 1 over AD minus BC times D, negative B, negative C, A. Okay, that's how you get matrix inverse. So the matrix inverse is going to be the same size as the original matrix, so 2 by 2. And so you can't just divide a matrix, you have to actually multiply by the inverse. So let's now work these out with actual matrices. So then we'll have x1 dot, x2 dot equals, we're going to have to do M inverse times C. So we'll say M11, M12, M21, M22 inverse times the C matrix, C11, C12, C21, C22 times X, X1, X2. Plus, we'll need M11, M12, M21, M22 inverse times tau 1, tau 2. And then finally, minus M11, M12, M21, M22 inverse times G1, G2. Now we have here, this is A. This is B. This is x. This is x dot. And this is u. And then this stuff here is extra. We have to include it because this is not a linear system. Here is a Simulink model of the system. You can see we're going to get theta 1, theta 2, then, so all of the red stuff here is theta 2, all of the blue stuff is theta 1, and the purple stuff is things that are shared by both of them. So if we run this, let's watch the behavior. You can see that it swung back and forth a lot, and since there was no friction in the system, it just kept swinging. So looking at plots of position, velocity, and acceleration, we can see that it appears to be an undamped system, which is correct because we didn't have any friction in it. And then you can see that theta 2 flops around a lot more than theta 1. So this is reasonable.